Hello everyone. In this video, I explain uh, the basic trigonometric and inverse trigonometric forms. So previously, based on the derivatives of six basic trigonometric functions, we found the corresponding integral formulas. And when we did this list, we noticed that some of the integral formulas were missing at that time. So for example, we don't know what the integral of tangent x so far. We don't know what the integral of cotangent x or secant x or cosecant x. Now that we have learned that how to work with the basic logarithmic form of integrals and we have some more information about the integrals, we can find the integrals of missing trigonometric functions. So let's start with the integral of tangent x dx. In order to find integral of tangent x dx, we use the basic trigonometric relationships. So tangent x can be written as sine x over cosine x dx. So in this case, we know that, we notice that this is a basic logarithmic form. So let me just remind you what is a basic logarithmic form is if you have 1 over fx. So fx is in the denominator and you have the differential of fx, then integral of this overall form would be ln of absolute value of fx plus c. So in this case, we notice that our function is cosine x. And if we want to find the differential of cosine x, that would be negative sine x dx. We don't have a negative here, but we can make the negative. So we can add a negative. And so in order to make it positive, we have to have another negative. So negative times negative is positive. Thus, we have this form 1 over fx and differential of fx. So it means our integral should be negative ln of absolute value of cosine x plus c. Similarly, we can find the integral of cotangent x. So in this case, again, we start with writing the basic forms. So cotangent x is equal to cosine x over sine x dx. Again, we notice that here we have our function as sine x and the differential of the function is cosine x dx. And we have this logarithmic form. So applying the logarithmic form, the integral should be ln of absolute value of sine x plus c. Thus, we found our two integral formulas. So one for the tangent x and another for cotangent x. Similarly, we can find our missing formulas for secant and cosecant. In order to find this, I have to be a little bit clever. So I'm gonna multiply and divide by this factor secant x plus tangent x, and I'm gonna divide by secant x plus tangent x. So I'm not changing anything about this function. So I'm just multiplying and dividing by secant x plus tangent x. The benefit of adding this factor is that, so now if we think about it, so our fx is in the denominator, so secant x plus tangent x, and then on the top in the numerator we have the differential of our u. So differential of this would be secant x tangent x plus secant square x dx. So we have this basic logarithmic form, reciprocal of a function, and the differential of the function. So it means the integral of this overall should be ln of absolute value of our function that's in the denominator plus c. Using the same approach, we can find the formula for cosecant x, integral of cosecant x. We multiply and divide by cosecant x minus cotangent x, and we notice that if we have our function u is equal to cosecant x minus cotangent x, then the differential should be, so for cosecant x we have negative cosecant x, cot x, and the derivative of cotangent x is negative cosecant square x. So this becomes positive cosecant square x. And since we are finding the differential, so times dx. Hence, we have this form reciprocal of the function and times by differential of the function. So it means our integral should be ln of absolute value of the function, which is cosecant x minus cotangent x plus c. Therefore, from the above discussion, we got the four new formulas for our basic trigonometric forms. So now we're going to solve some example problems using all these trigonometric forms. In first example, we notice that we have x times secant square x squared dx, and the angle is x squared, and we notice that we can make the derivative outside. So it means we have to use some kind of substitution here. So rewriting this, I notice that if I plug in x squared is equal to u, and then the differential of u would be du, which is x 2x dx. So we can make that here easily. So we just need to multiply by 2 and divide by 2. So if we do this, in the next step we notice that we have secant square of some new variable u du, and we already know that integral of secant square u du would be tangent to u plus c. So in this case, our u is x squared. So thus we got half. So tangent u is x squared plus c. So in the next one, so we have tangent 2x over cosine 2x. So recall that we have a trigonometric formula for, so if you have tangent and secant together, so tangent u secant u du equals secant of angle plus c. So we can easily make here secant using the relationship that 1 over cosine 2x is equal to secant 2x. Thus, we rewrite this as tangent 2x times secant 2x dx. Notice that here we have x, but here we have 2x and 2x. It means we need to do the substitution so that we can make this in the form a function and its differential. So if we use the substitution u is equal to 2x, it means the differential needs to be 2 times dx. So that means we need to multiply and divide by 2. So in the next step, I'm going to multiply and divide by 2 in order to make 2 dx. Now we can use our this formula. So we have the form secant 2x, tangent 2x, and the differential of our angle. So it means the answer should be equal to secant of angle plus c. So thus we get, let's do a few more examples to get some more practice. So for the next problem, I recognize that I have e raised to power negative x here and also e raised to power x in the denominator. So I'm just going to rewrite it first in the form. So I just moved this ex in the numerator, and if you remember, so we have the exponent rules that if you have x raised to power n, and if you bring this up, so the power is going to be the negative of n. And also today we learned that integral of secant x dx is equal to ln of secant x plus tangent x plus c. So we're gonna use this formula because I can recognize that I can make something like secant of an angle and differential of that angle form here as well, because we have angle as e raised to power negative x, and all we need is the differential of this angle. So if we think about, so let's say our u is negative x. If we think about the differential of this, so it would be, so derivative of e raised to power negative x would be e raised to power negative x, and then we have a negative sign for negative x, negative 1, right? And times dx. So all I need is a negative sign here in order to make the differential of u. So this is my u, and in order to make du, we just need a negative sign. So let's bring that negative sign here. Thus, we got this nice form here now. So we have secant of u and we have du. So now we can just use our integral formula and we get, so integral of secant of u would be ln of absolute value of u, and u is absolute value of secant of u, which is e raised to power negative x, plus tangent e raised to power negative x plus c. So in next one, we have a definite integral and we need to evaluate the value of this integral. So we start this problem by writing this as two fractions. After splitting this function, we notice that 1 over sine x is cosecant x and 1 over cosine over sine is cotangent x. And we know the integrals for cosecant x. So integral of cosecant x is given by ln of cosecant x minus cotangent x plus c. Similarly, integral of cotangent x is given by ln of absolute value of sine x plus c. So using this we get, so in this case we get ln of cosecant x minus cotangent x, and then we have to use the limits from pi over 6 to pi over 4. Similarly for cotangent x, we got ln of sine x and the limits from pi over 6 to pi over 4. So let's now plug in the limits. So we will do upper limit minus lower limit and upper limit minus lower limit. So, ln of, so cosecant pi over 4 is square root of 2 minus cotangent pi over 6 is 1 minus, so cosecant pi over 6 is 2 minus cotangent, sorry, here it's pi over 4 is 2. Cotangent pi over 6 is square root of 3 plus ln sine pi over 4 is square root of 2 over 2 and ln sine pi over 6 is 1 over 2. So if you want, so when you know the values are positive, you can just put the bracket, or if you are not comfortable with that, you can just keep using your absolute signs. Now we can combine some of these terms together into one log. So we know that ln of product is ln m plus ln n, and if you have division, so that means ln m minus ln n. So if you have subtraction between two ln terms, you can bring them together as a division. If you have addition between two ln terms, you can bring them together as a multiplication. Thus, since this and this is a positive term, so we're gonna multiply the inputs of ln in here, the arguments. So it's gonna be, so square root of 2 minus 1 times square root of 2 divided by 2. And for all the terms that are with the negative signs, they can go in the denominator. So it would be 2 minus square root of 3 times half. And we notice that 2 and 2 gets cancelled and we can combine the other terms. So we get ln of, so square root of 2 times square root of 2 is 2 minus square root of 2, and in the denominator we get 2 minus square root of 3. So that is our answer, or you can write it in the decimal form. So it's approximately 0.782. Therefore, in this video, we learned how to solve the problems involving basic trigonometric forms, and you can always use the substitution rule. You can use to see if you have the like angle and its differential in the equation, and you can just do some substitution and use the formulas accordingly. I hope you enjoyed this video. So in the next video, I will explain the basic inverse trigonometric forms. So please do watch that video as well. Thanks for watching.